Your database is dying under writes, so you add a read replica. Nothing happens. You add 3 more. Still nothing. Of course, nothing happened. A read replica takes 100% of your writes and adds work. It just also serves reads. There is no number of replicas that makes writes faster. The only real answer is to stop putting all the data on one machine. That's sharding, and today we're building it from first principles. Why the obvious hash function is a trap, how consistent hashing actually works, and how Notion tripled their database fleet with zero downtime. By the end, you'll know which decision here is genuinely irreversible, and why the honest advice is usually not yet. Let's be precise about what actually breaks, because the database is slow is not a diagnosis. You have one primary. Every write in your entire product goes through it. Reads you've already handled. The replicas take those, and that scaling works, genuinely up to a point. But look at what a replica actually does. It receives and applies the full write stream, all of it. Adding replicas increases the total write work in your system. It does not divide it. Your write ceiling is exactly one machine's write ceiling, and it always was. That ceiling is made of write IOPS, connection count, and the maintenance tax, vacuum, backups, and schema migrations all get slower as the table grows, and they compete with live traffic for the same disk. Notice that adding a replica makes the maintenance tax worse, because now you're maintaining 4 copies. Writes stay exactly the same. For calibration, the same anchor we used last time. UPI is running around 23.7 billion transactions a month as of mid 2026, roughly 760 million a day. Call it 8,800 a second on average, with peaks well above that. Here's the honest read on that number. 8,000 writes a second is not obviously a sharding problem. A well-tuned Postgres on modern hardware can be in that territory. What forces the split isn't usually the rate. It's the total size, the maintenance tax on a table with tens of billions of rows, and the fact that a single machine is a single blast radius. Hold on to that. We're going to come back to it at the end, and it's going to change the recommendation. Before we split anything, let's kill the 3 things everyone tries first, because 2 of them are actually good advice, and the third is a trap that a lot of people fall into. Attempt 1. Buy a bigger machine. Do this. Seriously, do this first. Vertical scaling is boring, it's instant, it requires no code changes, and the machines available now are genuinely enormous. But it has 2 properties you need to plan around. The price curve has an elbow in it. Capacity is roughly linear in cost right up until it isn't. And past that elbow, you're paying multiples for increments. And the top of the curve is a hard stop. There is a biggest machine, and when you reach it, you have no next move. The question is never, does this work? It's, how long does this buy me? And what am I building during that time? Attempt 2. Read replicas. Also do this. Also doesn't touch your problem. We just covered why. Every replica carries the full write stream. But there's a second cost worth naming. Replication lag. The moment you serve reads from a replica, some fraction of your reads are stale. Usually milliseconds. Under write pressure, which is exactly when you needed the replica, it stretches. And the classic bug falls right out of that. User posts a comment. The write goes to the primary. The redirect reads from a lagging replica. Comment isn't there. Now you're writing read your own writes logic. And that's real complexity you took on. Attempt 3. And this is the trap. Hash key modulo n. This is the obvious answer, and it is the one almost everyone reaches for. Hash the key. Take it modulo the number of servers. Done. It distributes beautifully. It needs no lookup table. It's one line. Now add a machine. Watch what happens to a key. It used to live at hash mod 4. Now it lives at hash mod 5. Those 2 answers agree only by coincidence. and coincidence here has probability of about 1 in n. Going from 10 servers to 11 relocates roughly 90% of your data. Not 10%, 90. To add 10% more capacity, you move almost everything you own across the network, while serving live traffic, with every cache in the system simultaneously wrong. That's not a resize. That's a migration of the entire dataset, triggered by adding one box. And if that formula looks familiar, it should. Last episode Kafka, partition, hash, key, %num partitions, same function, same property, which is exactly why increasing a Kafka topic's partition count breaks key to partition ordering, and why Kafka won't let you decrease it at all. It's not a Kafka quirk, it's modulo. So the requirement is now sharp. We need a mapping from keys to machines where adding a machine moves only the keys that machine takes over and nothing else moves. Here's the whole idea, and it's smaller than people expect. Everyone treats which machine holds this row as one question. It's two, and the entire problem comes from collapsing them. Mapping 1, key to logical shard, a pure function, deterministic, fixed forever, never changes. Mapping 2, logical shard to physical machine, a lookup table, just data. You can change it whenever you like. That's it. That's the indirection. And everything else in this video is a consequence of it. Cause now think about what adding a machine costs. The key to shard function doesn't change. It can't, it's frozen. So no key ever changes which logical shard it belongs to. Adding capacity is purely editing the second mapping. Take some logical shards, point them at the new box, move only those. Nothing else in the system knows anything happened. The trick is to pick a logical shard count that is much larger than your machine count and never change it. Notion did exactly this, and their numbers are worth memorizing because they're a masterclass. In 2021, they sharded Postgres into 480 logical shards, sitting on 32 physical machines, 15 logical shards each. In 2023, they needed more capacity. They went to 96 machines, 5 logical shards each. 3 times the fleet. The logical shard count did not move. Not one row changed which logical shard it belonged to. And why 480? Because it's a highly composite number. It divides evenly by 32, by 40, by 48, by 60, by 96, by 120, by 240. Every one of those is a fleet size they can grow into with perfectly even distribution and no remainder. That's not a detail, that's the design. Pick a number with a lot of factors, pick it once, pick it far too big, and you've bought yourself a decade of resizes that are just configuration changes. Figma made the same split explicitly and drew a lesson out of it that's worth stealing. They separated logical sharding at the application layer from physical sharding at the Postgres layer, and this is the good part, they rolled them out separately. Logical sharding went first, using database views, which is cheap and reversible. The physical failover, which is the genuinely dangerous step, came later and on its own. That's the pattern. Decouple the risky operation from the cheap one so you're never testing two new things during the same incident. So where does mapping 2 actually live? 3 options, and you're picking one whether you realize it or not. In your application, a library that knows the routing table, 0 extra hops, 0 extra infrastructure. But every service in your company needs that library, and now they all need to upgrade in lockstep when the table changes. In a proxy, Vitis in front of MySQL, Figma's DB proxy in front of Postgres, Pigbouncer doing the simple version. Your app talks to what looks like one database. The proxy owns routing and can also do connection pooling, load shedding, and query rewriting. Cost, a new tier to run, and a new thing that can be down. In the database, Citus, DynamoDB, Cassandra, MongoDB. The engine shards natively, and you mostly don't think about it. Cost. You are now married to that engine's opinions about what you are allowed to query. There is no free option here. But notice all three implement the same two mapping idea. They just disagree about who holds the table. Now, the fixed logical shard approach assumes you know your machines and change them deliberately. Sometimes that isn't true. In a cache fleet or a peer to peer store or anything where nodes join and die on their own schedule, you need a mapping that resizes itself without a central table. That's what consistent hashing is for. It came out of MIT in 1997, Kargar and colleagues, originally for distributed web caching. Akamai was built on it. Here's the construction. Take your hash space and bend it into a circle, so the largest value wraps around to 0. Hash each server onto the ring. Its position is just the hash of its name. Now hash each key onto the same ring. The rule: a key belongs to the first server you meet, walking clockwise from where it landed. That's the entire algorithm. Now watch the property that makes it worth knowing. Add server E. Only the keys sitting in the arc between E and its counterclockwise neighbor change hands. They used to walk clockwise past that spot to C. Now they stop at E. Every other key on the ring is completely unaffected. On average, you move k over n keys. Your data divided by your server count, instead of all of it. Remove a server and the same thing happens in reverse. Its arc falls to its clockwise neighbor, nobody else moves. That's the win, and it's the entire reason this algorithm is famous. Now the part the tutorials rush past, because plain consistent hashing has a real problem. Server positions are random hashes, and random points on a circle are not evenly spaced. With a small number of servers, you routinely get one machine owning a third of the ring while another owns a sliver. Random placement gives you load imbalance, roughly on the order of the square root of what you'd hope for. With 100 servers, meaningful skew. With 10, sometimes brutal. And it gets worse when a node dies. Its entire arc lands on exactly one neighbor, which is now doing double work and is next to fall over. The fix is virtual nodes. Instead of hashing each server once, hash it many times. Server A gets tokens at A1, A2, A3 and so on, scattered all over the ring. Each physical machine now owns many small arcs instead of one big one. Two things fall out immediately. Distribution gets much smoother because you're averaging over many samples instead of trusting one. And when a node dies, its many small arcs get inherited by many different neighbors. So the load from a failure spreads across the cluster instead of landing on one victim. Amazon's Dynamo paper in 2007 put this in front of the industry, and it's how Cassandra, React, and DynamoDB's ancestors all work. Now, here's the caveat, and it's the most useful thing in this segment because it contradicts what nearly every consistent hashing tutorial online still tells you. The tutorials say more virtual nodes is better, use hundreds. Cassandra shipped a default of 256 tokens per node for years on exactly that reasoning. In Cassandra 4.0, the project cut that default to 16. Because smoothness of distribution is not the only cost function. High token counts made everything else worse. Bootstrapping a new node meant streaming from an enormous number of ranges, repair times ballooned, and the sheer number of ranges drove up CPU and made operations painful. 16 tokens paired with a smarter token allocation algorithm rather than pure randomness gave them balance that was good enough with operations that were dramatically better. The lesson generalizes past Cassandra. The theoretically clean answer, more randomness, better distribution, lost to an operational reality that the theory doesn't model. When you see a config default change by a factor of 16, that's what happened. Everything so far has been about how you map keys to machines. This segment is about what you hash, And I want to be blunt. This is the decision that determines whether sharding was a good idea. Change your hash function later. Annoying migration. Change your machine count. Routine. Change your shard key later. You are rewriting every table, every query, and a meaningful fraction of your application logic. And you will do it while the thing is running. So let's do it properly. 3 strategies first, then the rule for choosing. Strategy 1. Range sharding. Split by ordered ranges of the key. Shard 1 holds A through F, shard 2 G through M, and so on. The good range queries stay fast and local. Give me every order in March is one shard. Splitting a shard is easy. Cut a range in half. The bad, and it's severe. Range is hotspot by construction. Shard by timestamp, and every single write in your system goes to the newest shard because now is always in the last range. You've built a sharded system where writes are not sharded at all. Same for auto increment IDs. Same for anything alphabetical because names are not uniformly distributed. Strategy 2. Hash sharding. Hash the key first, then map the hash. Distribution is excellent, that's the whole point. The cost is the exact mirror image. You destroyed ordering. Adjacent keys land on unrelated shards, so any range query becomes a query to every shard. Every order in March now hits all 96 machines. Strategy 3. Directory sharding. Keep an explicit table saying where each key lives. Maximum flexibility. You can move an individual noisy tenant to its own machine, which neither of the other two allows. The cost. That table is now on the hot path of every query. It's a thing to cache, keep consistent, and lose. Now the rule. A shard key has to satisfy 3 requirements at once. 1. It must spread writes evenly. High cardinality, no dominant values. 2. It must appear in your most common queries. If the key isn't in the where clause, the router doesn't know which shard to ask, so it asks all of them. 3. It must keep data that's read together on the same shard. Otherwise, your single logical operation becomes a fan out. You will usually not get all 3. Choosing a shard key is choosing which of these to sacrifice, for which queries. That is the whole job. Discord's message storage is the best worked example in public, so let's walk it. The obvious key for chat messages is channel ID. It satisfies requirement 2 perfectly. Every query is give me the recent messages in this channel. And requirement 3 perfectly, because the channel's messages belong together. It fails requirement 1 badly. Channel sizes are not remotely uniform. Most channels are tiny, and some are enormous and never stop growing. Discord hit real errors from partitions exceeding 100 megabytes, which is where Cassandra starts to suffer. Note the shape of that failure. It isn't that the load was uneven at one moment, it's that the partition was unbounded. A busy channel's partition grows forever, so no matter how well balanced you are today, that key is a time bomb. The fix was a composite key, partition by channel ID, and a time bucket. They studied their own message patterns and found that 10-day buckets kept partitions comfortably under the 100 megabyte line. Look at what that buys. Requirement 3 still holds. A channel's messages for a given window are together. Requirement 2 still holds. The last 50 messages in this channel is one partition read, because the recent bucket is the current one. And requirement 1 is fixed, because partitions are now bounded by construction. A channel produces a new partition every 10 days, instead of one that grows without limit. That's the move to internalize. When a natural key is right for your queries but unbounded in size, bound it with a second component. On more, and it's a direct callback. Last episode we hit hot partitions in Kafka. One key far busier than the others. One consumer melting while the rest idle. Identical problem here, and the multi-tenant version is the one that bites hardest. You shard by tenant ID, it's beautifully distributed across 10,000 customers. And then you land one enterprise customer who is bigger than every other tenant combined. Now, one shard is your whole problem, and the mapping has no way to split them because they are one key. Go look at your own data and compute the ratio between your largest tenant and your median tenant. That ratio is your hot shard risk, and you can measure it today. You've chosen a key, you've picked a logical shard count. Now you have to get a live production database from where it is to where you want it, without an outage and without losing a row. There's a standard playbook, it's 7 steps, and step 4 is the one everybody wants to skip. Step 1, build the new topology alongside the old. Nothing is routed to it, it just exists. Step 2, dual write. Every write goes to both old and new. The old path is still authoritative. The new one is a shadow. Your rollback here is one config flag, which is exactly the property you want. Step 3, backfill. Copy the historical data into the new topology in chunks, throttled, while dual writing continues. The tricky part is the seam between backfilled history and live writes. The usual answer is idempotent writes, so overlap is harmless rather than corrupting. Step 4, verify. Read from both, compare. Log every mismatch. Sit here. This is the step that gets cut when the project is late. And it's the only step that tells you whether the previous 3 worked. You are looking for the small stuff. A nullable column handled differently, a time zone, a race between backfill and a live update. Those don't announce themselves. They surface as a customer support ticket in 4 months, by which point the old data is gone. Step 5. Shift reads gradually, 1%, 10, 50. Watch error rates and latency at every step. Reads are the safe direction to move first, because if the new path is wrong, you serve some bad reads. Bad but recoverable. Nothing is lost. Step 6. Cut over writes, the genuinely irreversible moment. Everything before this was rehearsal. Step 7. Keep the old path alive. Longer than feels necessary. Deleting the old data is the last step, not part of the cutover. Notion's 2023 Reshard is a clean instance of this. They tripled the fleet from 32 to 96 machines. Their mechanism was PJ Bouncer. They added connection entries for all 96 new shards, but pointed them back at the existing 32 databases first. So the new topology existed and was being exercised while the data hadn't moved yet. Then they migrated traffic over gradually, verifying as they went. Notice the shape. Make the new topology real before making it different. Same instinct as Figma doing logical sharding before physical failover. Both teams found a way to test the new addressing scheme while the dangerous part hadn't happened yet. That's the transferable idea. Any large migration can be decomposed into a reversible part and an irreversible part, and the whole craft is doing them separately. Now the half of the video that actually matters, because sharding is the first technique in this series that makes your system worse along several axes permanently in exchange for the one thing you needed. 1. Joins across shards are gone. Your database cannot join 2 tables that live on different machines. That's not a limitation of your ORM, it's arithmetic. The rows aren't in the same place. So a join either becomes a scatter gather across shards, or it becomes application code pulling both sides and joining in memory. Or you denormalize so the join isn't needed. All 3 are worse than what you had. Denormalization is usually the right answer, and it means you're now maintaining consistency between duplicated copies by hand. 2. Fan-out queries inherit the worst machine's latency. This one deserves numbers. A scatter gather isn't done until the last shard replies, so your response time is the maximum across shards, not the average. Say each shard is well behaved. P 99 of 10 milliseconds, meaning only one request in 100 is slow. Fan out to 100 shards, and the chance that all of them are fast is not 0.99 to the 100th, which is about 37%. So, roughly 2 out of 3 fan out requests hit at least one slow shard. Your rare tail event is now the common case. This is tail latency amplification, and it's why just query all the shards quietly stops being acceptable as the fleet grows. 3. You lost transactions. Single node ACID across arbitrary rows was doing enormous amounts of work for you, and you probably never thought about it. Once rows live on different machines, a transaction spanning them needs two-phase commit, which is slow and worse blocking. If the coordinator dies at the wrong moment, participants sit holding locks waiting for a decision that isn't coming. What good teams actually do is design so transactions don't cross shards. Put the things that must be atomic together on the same shard deliberately as a schema decision. When you truly can't, you go to sagas and compensating actions, which, call back to last episode, is the same outbox and eventual consistency territory Kafka put us in. 4. Any query without the shard key hits every shard. If you shard users by user id and then need find the user with this email address, the router has no idea where to look. That's a 100 machine fan out to return one row. The fixes are real, but each costs you a global secondary index, which is just another sharded table keyed by email pointing at the shard. And it's eventually consistent, so it can lie briefly. Or a full denormalized copy of the data sharded the other way, which doubles storage and writes. Or you accept the fan out for genuinely rare queries. 5. Hot shards cannot be fixed with money. This is the one I most want you to remember. DynamoDB makes this beautifully concrete because the limits are published. A single partition tops out around 10 gigabytes, 3000 read units and 1000 write units per second. Adaptive capacity will lend a busy partition throughput from idle ones, which helps, but it cannot exceed those per partition ceilings. So you can provision a million write units at the table level, and a single hotkey still throttles at 1000. No amount of table level capacity fixes a hot partition on any system. It's a property of your key, not your budget. The fixes are all key design fixes. Add a component to bound or spread the key, salting, bucketing the Discord move, or pull the whale out into its own dedicated shard. 6. And the honest one. You probably shouldn't shard yet. Sharding is a one-way door that will consume a serious chunk of your engineering capacity. Figma's databases team spent the better part of a year on this, and they're very good. So exhaust the cheap options first, in this order. Fix your indexes, which is episode 1, and is astonishing how often it's the actual answer. Cache the hot reads. Move analytics off the primary, because it's frequently a reporting query, melting your production box. Archive cold data. Most tables are mostly history. Nobody queries. Use native table partitioning within one machine, which gets you smaller indexes and cheap bulk deletes with none of the distributed cost. Then buy the bigger machine. Every one of those is reversible in an afternoon. Sharding is reversible in a quarter, if at all. The right time to shard is when you have a specific measured ceiling with a date attached, not when the graph looks scary. So, the mental model to walk away with. Sharding is not more machines. Sharding is giving up the global view. Your database stops being one thing that can see all your data and answer any question about it, and becomes a fleet of independent databases that are each ignorant of the others. Every cost in that last segment is a bill for that one loss. Which makes the shard key the real subject of this video. It's the decision about which question stayed cheap, and every question you didn't put in that key gets more expensive forever. And that completes an arc worth naming. B trees were about minimizing disk trips. The log was about eliminating random writes. Sharding is about giving up the global view. 3 different disciplines. 3 different things you're willing to lose. Every storage system you'll ever evaluate is somewhere on those three axes. If you remember one line from this, the two mappings, key to logical shard, frozen forever. Logical shard to machine, edit whenever you like. Notion moved from 32 machines to 96 without a single row changing which logical shard it belonged to. That's not a clever trick. It's what happens when you refuse to collapse two decisions into one. Homework, two things. Both take an afternoon. First, pick your biggest table and work out what fraction of your queries filter on your candidate shard key. If the honest answer isn't nearly all of them, that key will fan out and you need a different one. Better to know now than after the migration. Second, compute the ratio between your largest tenant and your median tenant. That single number is your hot shard risk. And if it's in the hundreds, shard key choice is going to be the hardest part of the project. I'm Name. This is the Tech Intern. See you in the next one.